Bismillahirrahmanirrahim. Assalamu alaikum students. Welcome to our 20th lecture of MTH108 Business Math 1. Today we will continue with our 9th chapter, which is about matrix algebra. We have started this chapter in our last lecture. So let us look at the objectives of the chapter again. The objectives are to provide an understanding of the nature of the matrix and matrix representation of data, to provide an understanding of the algebra of matrices, and to provide applications of matrices and matrix algebra. And what are the main topics of this chapter? About the introduction of matrices, the special types of matrices which we have seen in our last lecture, matrix operations, determinant, inverse of a matrix, and some applications. What we have studied in our previous lecture, we have studied the definition of matrix, why do we need a matrix, and the proper definition. Some basic facts about the matrices, which mainly includes the notation of a matrix, elements, the dimension, and the dimension or order of the matrix. We have also studied some special types of matrices, which mainly include the row matrix, column matrix, zero matrix, identity matrix, square matrix, and diagonal matrix, and the transpose of a matrix and how we can calculate it. Further, in our last lecture, we have studied two matrix operations, that is the matrix addition and the scalar multiplication. And by using the scalar multiplication, we have also defined the matrix subtraction and the properties of matrix operations. Today we will study our third property of matrix operation, which is about matrix multiplication. And further we will study about the representation of systems of equations with the help of matrices. Okay, we start our lecture with the matrix multiplication. Then assume that we are provided with a matrix A having the dimension m by n, and we want to multiply this matrix with a matrix B, the matrix B having dimension n by p, and we are interested in the product of this matrix A and B. Then we define the product C as to be a matrix of order m by P, whose entries C, I, J in ith row and jth column are obtained with the following rule. That is, the sum of products formed by multiplying in each order formed by multiplying in order each entry in row 1 of A by the corresponding entry in column J of B, in row I of A by the corresponding entry in column J of B. What do we mean by this statement, that how do we obtain the entries of our product matrix C? From this definition, we know that what will be the order of the product matrix. That is, we are given with two matrices with orders m by n, and the second with order n by p, and the resultant will have order m by p. Okay. Now, what are the properties of this matrix multiplication? First we will look at them, and then we will see with the help of examples that how we can multiply our matrices. The matrix product AB is defined when rows of the matrix A is equal to the columns of the matrix B. What do we mean by this? That is, let's say our matrix A has order m by n, that is m rows and n columns, and our matrix B has order n by p, that is n rows and p columns. Then the product is possible when the columns of A is equal to the rows of P. So the product is possible when the columns of A, that is n, is equal to the rows of B. That is, this number should be the same. Only then the two matrices can be multiplied, and the resultant matrix will have the order, that is number of rows of A, and number of rows and number of columns of B. Now the second property of matrix multiplication is that the resultant product will have the order of row of A, that is row of A is M, and the column of B. The column of B is P. So the resultant matrix will have the order of row of A and column of B. And the third property is that order of multiplication matters. What do we mean by this third property, that the order of multiplication matters? We will see in our examples that what happens when we take the product AB and what happens when we take the product BA. So now we look at some examples. For example, we have our matrix A as 2, 4, 3 and 1, and the matrix B as -4 and 2, and we want the product of these matrices A, B. So first we have to look at the order of our matrix A. This is a square matrix of order 2 by 2, that is number of rows is 2 and number of columns is 2. Now matrix B is a column matrix with 1 column and how many rows? 2 rows. Now the product AB is possible only when number of columns of first is equals to number of rows of the second, which is 2 in both the cases, which means that in this case we can take the product AB, and the product or the resultant matrix will have the order number of rows of first and the number of columns of second. That is, the resultant matrix will be a column matrix of order 2 by 1. That is, the matrix will be a column matrix with 2 entries C11 and C21. And now we have to find these 2 entries C11 and C21. Okay, now C11, first we will write these 2 matrices AB together as 2, 4, 3, 1 and B is -4, 2. Now C11 is obtained when the first row is multiplied with the column of the second. That is, first row by mean A11 is multiplied by B11 and A12 is multiplied by B21 and added together. So what do we obtain? This is nothing but A11 into B11 plus A12 into B21, and now we put the values. We obtain 2 into -4 plus 4 into 2, which is equals to -8 plus 8, 0. Okay. The second entry C21 will be obtained by multiplying the second row with the column of matrix B. Since there is only one column, we have to multiply with this column, which means that in terms of elements, the entry A21 multiplied by the entry B11 plus the entry A22 multiplied with the entry B21, which is, now putting the values, 3 into -4 plus 1 into 2, which is -12 plus 2 is -10. So our matrix C, the resultant of the product of 2 matrices A and B, is 0 and -10. Now consider these 2 matrices A and B again, and now we want the product BA in the order BA. Now for this we have to first check that is this product allowed or not, can we take this product or not. How we will check it? By looking at the orders of both the matrices B and A. The matrix B has order 2 by 1 and the matrix A has order 2 by 2. Number of columns of B is different from number of rows of A, which means that we cannot take the product BA. This is not possible. And by our third property of the matrix multiplication, we have stated that the order of multiplication matters. And here we have seen in our example that in our example 1 we have multiplied with the order AB, and in our second example we have multiplied with the order BA, and with the order AB it was possible to take the matrix multiplication, and with the order BA it was not possible to take the matrix multiplication, which means that the order of the matrices written really matters. That is, AB in this case is different from BA. Now we look at our third example. Suppose we have a matrix A given as 2, 1, minus 6, 1, minus 3, 2, and we have our matrix B as 1, 0, minus 3, 0, 4, 2, minus 2, 1, 1. Okay. Here I have used these square brackets to represent our matrices. Okay, now our matrix A has order, it has 2 rows and 3 columns, 2 by 3. Our matrix B is a square matrix of order 3 by 3, that is 3 rows and 3 columns. And we are interested in finding the product AB, which means that first we have to look that whether the product is allowed or not, that is 2 by 3 and 3 by 3. Now the number of columns of A is same as number of rows of B. This means that the resultant matrix C will have the order, what is left here, 2 and 3, will have the order 2 by 3. That is, the resultant matrix C will be a matrix of 2 rows and 3 columns. C11, C12, C13, C21, C22, C23. And now we have to find all these 6 entries. Okay, first we write our matrices AB side by side. 2, 1, minus 6, 1, minus 3, 2, and our matrix B 1, 0, minus 3, 0, 4, 2, minus 2, 1, 1. Okay, now our entry C11 will be the first row of matrix A multiplied with the first column of matrix B. That is, the first row with the first column. And how? That this entry will multiplied with this, plus this entry will multiplied with this, plus this entry will multiplied with this, which is 2 into 1, plus, and all these entries are added in the end, plus 1 into 0, plus minus 6 into 2. And now by solving we obtain 2 minus 12, this is minus 2, 2 plus 12, which is 14. Okay, now the entry C12 will be obtained by multiplying the first row of matrix A with the second column. That is, C12 will be first row, which means this row, with the second column. If we look at our index, C12 means the first row should be multiplied with the second column. If we look at our element C11, which means that the first row should be multiplied with the first column. So first row is 2 into 0 plus 1 into 4 plus minus 6 into 1, and simplifying we obtain 4 minus 6 is minus 2. Okay, and now we have to find the entry C13. Okay, what are our matrices? We write them again so that we can easily find the product entries. Our matrix A was 2, 1, minus 6, and second row 1, minus 3, 2. Matrix B was 1, 0, minus 3. Second row is 0, 4, 2, and third row is minus 2, 1, 1. And we have to find our entry C13, which means that first row and third column, that is first row with third column. And how we multiply it? As 2 into minus 3 plus 1 into 2 plus minus 6 into 1, which is minus 6 plus 2 minus 6, which is equals to minus 10. Our entry C21. C21 means we have to multiply our second row, that is second row, with first column. And how? First entry with first, added with second entry with second, added with third entry into third entry, and then simplified. We obtain minus 3. Our entry C22 will be second row, that is C22 means second row and second column. And how? First with the first one, added with second with the second one, added with the third one. We obtain minus 12 plus 2 is minus 10. And our last entry C23, which means that second row and third column, that is first one with first, added with second entry, multiplied with second entry, added with third entry, multiplied with third entry, which is minus 3, minus 6 plus 2, which is minus 7. And now we can write our product matrix C as C11 was 14, C12 was minus 2, C13 minus 10, C21 is minus 3, minus 10 and minus 7. So this is our product matrix of order 2 by 3, that is 2 rows and 3 columns. Okay, now we ask ourselves that what will be the product of the matrix D is equals to BA, that is when we change the order of our matrices B and A. Now the matrix B has order 3 by 3 and the matrix A has order 2 rows and 3 columns 2 by 3. Now the number of columns of first is different from number of rows of the second, which means that BA is again not possible. We cannot take the product of the matrices B and A when they have the orders 3 by 3 and 2 by 3 respectively. Now let us look at some more examples of the matrix multiplication. We have our matrix A having order 3 by 5 and our matrix B having order 5 by 3. And we want to know that is the product AB exist, then in this case the product AB will be 3 by 5 and 5 by 3. The number of columns of A is same as number of rows of B, so the resultant matrix C will be a matrix of order 3 by 3. Can we also find the product BA? That is when we change the order. In this case, the matrix B has order 5 by 3 and the matrix A has order 3 by 5. Now the number of columns of B is same as number of rows of A. This implies that the resultant matrix D can be obtained by taking the product of matrix BA having these orders, and the order of the resultant matrix D will be 5 by 5. So these examples clearly tells us that the order of multiplication really matters. That is, a matrix AB it cannot be equal to the matrix BA. In our previous examples, we have seen that there were cases when the product AB was defined, but when the product BA was not possible to find. In this example, we have seen that both the directions are possible to find. That is, both the products AB and BA are possible to find, but the products have matrices of different orders and thus entirely different matrices. So the order of multiplication really matters, and we have to be extra careful when multiplying two matrices. Let us consider one more example. We have our row matrix 1, 2 and 3. This is a row matrix with 1 row and 3 columns, and we have our column matrix 4, 5, 6. That is, it is a column matrix with 3 rows and 1 column, and we want to find that does the product of these two matrices exist or not. If it exists, what will be the order of the product matrix? Let us call them A and B, and question is, C exist or not? If exist, then what is the order of C? Okay, how we can find it? Now, since the matrices A and B can be multiplied, why? Because the columns of A is same as number of rows of B. So the resultant matrix C will be a matrix of order 1 by 1, that is 1 row and 1 column. And how we will obtain it? It will have only entry C11, and C11 will be obtained by multiplying the first row of A with the first column of B, that is, their respective elements multiplied and then added, which means that 1 into 4 plus 2 into 5 plus 3 into 6, and then we will simplify it to obtain plus 18, which is 32. So the resultant matrix is a matrix of order 1 by 1, that is 1 row and 1 column, and the resultant product exists having order 1 by 1. Now, what can we say about the product BA? Does this product BA exist or not? If it exists, what will be the order of our product matrix? Now, the matrix B has order 3 by 1 and the matrix A has order 1 by 3. The number of columns of B is same as number of rows of A, so the product of BA exists. And what will be the order of this matrix D? It will have the order 3 by 3, that is 3 rows and 3 columns. How? We will see it in our next example. That is, we have our matrix B as our column matrix 4, 5, 6, and matrix we call matrix A as our row matrix 1, 2, 3, and we have just said that the product D is equals to BA will be a matrix of order 3 by 3. That is, the matrix D will be a matrix having 9 entries, that is D11, D12, D13, D21, D22, D23, D31, D32, D33, a matrix of order 3 by 3. And how we will obtain our entry D11, that is the first row multiplied with the first column, which is 4 into 1. Okay, the entry D12, that is the first row multiplied with the second column, which is 4 into 2. D13 will be obtained by multiplying the first row, which is 4, to the third column, which is 3. Now D21 will be obtained by multiplying our second row with the first column. D22 will be obtained by multiplying second row with second column, and D33 with second row and third column, D23. D31 with third row and first column. D32 is third row and second column, and D33 is third row and third column, which after simplification we obtained 4, 8, 12, 5, 10, 15, 6, 12, 18. So this is our matrix obtained by the product of matrix, obtained by the product of our matrix BA of order 3 by 3. Now one more example. Suppose we are provided with the cost vector, that is, suppose that the prices for products A, B and C, we have 3 products A, B and C, and their prices are given by the price vector P is equals to 2, 3, 4, that is the price of the product A, the price of the product B and the price of the product C. And if the quantities of the products A, B and C that are purchased are given by the column vector, that is Q represents the column vectors of the quantities of the products A, B and C which are purchased as 7, 5 and 11, that is the number of units purchased of product A, number of units purchased of product B and number of units purchased of product C. And we are asked to find the cost vector, that is, cost is defined as price into quantity. So we are asked to find the cost vector. Can we find the cost vector? Because we have written our price vectors and our prices and quantities in the form of matrices, and to find that the cost vector we can simply use the rule of matrix multiplication. That is, our price vector is a row vector of 1 row and 3 columns, and our quantity vector is a column vector of 3 rows and 1 column, which means that the cost vector can be obtained, and the cost vector, since these two are same, so our cost vector will be a vector having 1 row and 1 column, that is 1 row, row of the first and column of the second, which is C11. And how we will obtain our C11? Simply by multiplying the first row of price vector with the first column of our quantity vector, that is multiplying the respective components and then adding them, which means that 2 into 7, here we have only 1 row and 1 column, so 2 will be multiplied by 7, 3 will be multiplied by 5, 2 by 7, 3 by 5 and 4 by 11. and 4 will be multiplied by 11, and all these added together we obtain 14 plus 15 plus 44, which is equals to 73. So this is our price vector 73. Okay, now again we ask ourselves that is QP possible? That is, Q will have order, Q has order 3 by 1 and P has order 1 by 3. The number of columns of Q is the same as number of rows of P. So we can also obtain our matrix QP obtained by the product of QP. We may call it as D, obtained by QP, and the matrix D will have order rows of first and the columns of second, that is 3 by 3. Now we have done enough examples of matrix multiplication, that in which case the matrix multiplication is possible, and if we reverse the order, can we also multiply the matrices or not, and some word examples. So we have seen that we can also find our matrix QP, denoted as D, obtained by of order 3 by 3. What will be that matrix 3 by 3? What will be we have already solved our matrix cost vector C, and now we are interested in finding our matrix D, which is obtained by the product of matrix Q and P. Our quantity vector was 7, 5, 11, and our price vector was 2, 3, 4, and the resultant matrix will have the entries will be of order 3 by 3 and will have 9 entries. So D11 will be obtained, that is D11, D12, D13, D21, D22, D23, D31, D32 and D33, and our D11 entry will be obtained by multiplying the first row with first column, that is 7 into 2. D12 will be obtained by multiplying the first row with second column, that is 7 into 3, and D13 will be obtained by multiplying the first row with third column. D21 will be obtained by multiplying the second row with first column, D22 by second row second column, and D23 by second row third column, D31 by third row and first column, D32 by third row, and this should be 3 here, and D32 by third row and second column, and D33 by third row and third column. And we can simplify it as 21, 28, 10, 15, 20, 22, 33 and 44. So this is our matrix QP. Now we have seen enough examples of matrix multiplication, that in which case the matrix multiplication is possible and in which case it is not. Now we will see some important properties of matrix multiplication. We have already used these properties, but now we will see them in detail. Our first property is that we have 3 matrices A, B and C. Then the order in which we group them, it does not matter. That is, either if we take the product of B and C first and then the product of the resultant with matrix A, or either we group them, that is, take the product of A and B first and then the resultant with the product C. This grouping of matrices when we have more than 2 matrices in matrix multiplication does not matter, and we call this property as associative property of multiplication, or associative property with respect to multiplication. Our second property says that we have 3 matrices, again A, B and C, is that we want to add these 2 matrices first and then multiply the resultant with the matrix A. Then this is same as taking the product and then the sum. That is, either we take the sum and then the product is same as product and then the sum. Similarly, if we want to add our matrices A and B first and then want to multiply with the matrix C, then this will be same as taking the product of matrix A with C, taking the product of matrix B with C and then adding them. These two properties are called distributive properties. Our third property says that we have 2 matrices A and B and we want to take their product, but we have our scalar k as well. Then either we take the scalar multiple of our matrix A first and then take the product with B, or we take our matrix A, we take the product of our matrix A with the scalar multiple of our matrix B, then this is same as k times AB. That is, if we have 2 matrices A and B and 1 scalar k, then either we take the product of our matrices and then take the scalar multiple, or if we take the scalar multiple of one of the matrix, for example k here or B here, and then take the product with the second matrix, this order does not matter, or this grouping does not matter. We obtain the same result. Okay. Our fourth property is about the product and transpose. Suppose we have our 2 matrices A and B, and the product is then taken with the transpose, then the transpose of the product is same as the product of the transpose taken in the reverse order. Here we have the transpose of the product, that is, we are taking the product first and then the transpose, and on the right hand side we are taking the transpose first and then the product. So transpose of the product is same as transpose of the product is same as product of the transpose but taken in reverse order. Taken in reverse order. Now our fifth property says that if we have a matrix A and the identity matrix I and we want to take the product, then we will always obtain our matrix A. Our sixth property says that we have a matrix A and we want to take the product of this matrix with the 0 matrix, then we will always obtain our 0 matrix. Our seventh property says that we have our identity matrix with some power p, which is nothing but our identity matrix with p times or p factors. Then the product of identity matrix with itself is identity matrix again, and continuing so on, the pth power of identity matrix is again the identity matrix. If we want to apply this result for some matrix other than the identity matrix, for example, if we have our matrix A, the matrix A should be a square matrix. Okay, and then the pth power of our matrix A will be taking the product of our matrix A p times, that is, we have p factors. So if we have a square matrix, then we can take some power of that matrix. How? By taking the product of that matrix, that power times with itself. For example, we have our matrix A as 1, 0, 1, 2. Now this is a square matrix of order 2 by 2, and we are asked to find A cube. That is, we have to find what basically? We have to find the product of matrix A with itself 3 times. Okay, how we can find it? We will take the product, or we will find the product by grouping our matrices. How? That is, we take our matrix A here and we group the second 2 matrices first. That is, first we will simplify this matrix, which is nothing but A square. So what is A square basically? First we have to find it. Now A square can be found because the matrix A multiplied with the matrix A has the same, satisfies the rule of multiplication. The rule of multiplication, that is number of columns of the first is same as number of rows, and the resultant matrix will be a matrix of order 2 by 2, that is the rows of first and the columns of second. Okay, how we will find this matrix? Our A11 entry, A12, A21 and A22, because the resultant matrix will be a matrix of order 2 by 2. So A11 entry means the product of first row with first column, that is first row with first column, which means that 1 into 1 and 0 into 1, and these entries added together. A12 means first row and second column, that is 1 into 0 and 0 into 2, and these entries added together. A21 means second row, that is 1 should be multiplied with something and 2 should be multiplied with something, with the entries of the first column, that is 1 should be multiplied with 1 and 2 should be multiplied with 1, and these entries added together. A22 has something to do with the second row, okay, and second column, that is 1 into 0 and 2 into 2, and these entries added together. So after simplifying, we obtain A square as 1, 0, 3 and 4. But we were asked to find A cube, which means that we have to multiply this A with A square again. Okay, so we write A again, 1, 0, 1, 2, and our A square, which we have just obtained. And now the resultant matrix will be a matrix of order 2 by 2. Okay, how? First row with first column, that is 1 into 1 plus 0 into 3. First row with second column, 1 into 0 plus 0 into 4. Second row first column, that is 1 into 1 plus 2 into 3. Second row second column, that is 1 into 0 plus 2 into 4. And after simplifying, we obtain 1, 0, 7 and 8. So in this way, if we are given with a square matrix, we can easily find the sum power of that matrix. How? By multiplying the matrix with itself with the power p time. So now we have seen enough examples that how we can find the multiplication of a matrix. Now we are interested in knowing an important property of matrix, which is the equality of matrix. That is, we are given two matrices and we are interested in knowing that when these two matrices are equal. So the definition says that the two matrices A and B are equal if and only if they have the same dimension. They have the same dimension and Aij is equals to Bij for each I and j. That is, for each I and j, which means that the entries should be same for every I and j, both I and j. What do we mean by this? By the equality of matrices, that is the corresponding entries should be same. Okay. How? For example, if we have a matrix 1, 1, a row matrix, and again we have one row matrix 1, 1 and 1, are these two matrices equal? Both are row matrices. This matrix have order 1 by 2 and this matrix have order 1 by 3. And the definition says that the two matrices are equal if and only if they have the same dimension. And the entries should be the same. Here we'll see that the entries are same, that is all the entries are 1, but the dimension is not same. That is, one matrix has dimension 1 by 2 and the other matrix has dimension 1 by 3, which means that these two matrices are not equal. Though they have the same entries, but their order is not same. Okay. For example, if we have a matrix 1 plus 1, 3 by 2, 2.6 and 0, and we have second matrix as 2, 1, 12 and 0. Now we have to see that whether these two matrices are equal or not, we have to look at two things. First is the dimension and second is the corresponding elements. Here both the matrices have the same dimension, that is, both are square matrices of order 2 by 2. And now we have to look at the corresponding entries. The first entry A11 and the first entry B11. That is, A11 is same as B11, which is 2. Fine. The second entry A12 is 3 by 2 and the second entry B12 is 1. Now these two entries are not equal, which means that the given matrices are not equal. This example shows that even though the matrices have same order, but their corresponding entries are not equal, which means that the given matrices are not equal to each other. Though we have our entry A22, which is 0, which is same as B22, but this entry A12, B12 and the entry A21, B21, they are not equal, which means that our given matrices are not equal. One more example. We have our matrix 1, 1 and 1, 1. Now both the matrices have the same entries. Okay, fine. But what about the dimension? This is a row matrix of dimension 1 by 2, that is 1 row and 2 columns. And this is a column matrix of dimension 2 by 1, that is 2 rows and 1 column. Even though the matrices have elements or entries same, but they have different order, that is, their orders are different. So these two matrices are not equal. Now using this equality of matrices, we can solve our system of equations. A matrix equation basically defines a system of equations. For example, if we have a matrix with variables x, y plus 1, 2z and 5w, then the equality sign in between with the matrix 2, 7, 4 and 2. Suppose we are given with two matrices. On one side we have the matrix of constants, and on the other side we have a matrix of variables. And we say that this is a matrix equation. We have two matrices with equality sign in between, and we say that a matrix equation defines a system of equations. How? Since we are saying that these two matrices are equal, which means that both the matrices have same order. This matrix have order 2 by 2, and the second matrix also have order 2 by 2. And since these two matrices are equal, which means that their corresponding entries are also equal. That is, the entry A11 implies x is equals to 2. The entry A12 implies y plus 1 is equals to 7. The entry A21 implies 2z is equals to 4. And the entry A22 implies 5w is equals to 2. So this matrix equation has given us basically a system of equations. That is, we have 4 equations and 4 unknowns. And we can further simplify our equation 2, which gives us y is equals to 6. Our equation 3, which gives us z is equals to 2. And our equation 4, which gives us w is equals to 2 by 5. So once we are given a matrix equation, which means that we are given the matrices with the equality sign in between, which means that both the matrices have the same order and the corresponding entries are same. These type of matrices or matrix equation basically defines a system of equations. Now one more example. We are asked to solve the equation 2 into x1 x2 minus 3 4 is equals to 5 times 5 and minus 4. We are given with a matrix equation with the right side as the matrix of constants and with the left side as the matrix of variables. And we are asked to solve this matrix equation. First we will simplify the respective matrices. How? If we look at our leftmost matrix, we see that 2 is multiplied with the matrix, which is nothing but the scalar multiplication of the matrix with a scalar k is equals to 2. So we will solve this. If we obtain 2x1 and 2x2, that is, the scalar is multiplied with each entry of the matrix. The minus sign stays as it is, and we write our second matrix as it is equals to. Now the right hand side matrix is again can be simplified by using the scalar multiplication. That is, here k is equals to 5. So this scalar will be multiplied to each entry of the matrix, and we obtained 25 and minus 20. Now the left hand side can be simplified further, which is nothing but the subtraction of matrices, and we obtain as 2x minus 1, 2x1 minus 3 and 2x2 minus 4 is equals to 25 and minus 20. Now we have a matrix equation. On the right hand side we have a matrix of order 2 by 1, and on the left hand side we have a matrix of order 2 by 1. Since both the matrices have the same order, which means that their respective entries should be the same, which gives us our system of equations as 2x1 minus 3 is equals to 25 and 2x2 minus 4 is equals to minus 20. So again we have obtained a system of equation That is, we have two equations and two unknowns, x1 and x2, which we have obtained from our matrix equation. And these two equations can be further simplified. We obtain 2x1 is equals to 28, implies x1 is equals to 14. And the second equation gives us 2x2 is equals to minus 16, implies x2 is equals to minus 8. So, writing our system of equation in the matrix form is much easier to handle, and given a matrix equation with one side with the matrix of unknowns, we can obtain our system of equations. Okay, continuing further with our matrix equation, using this information we can represent our equation with the help of matrices. How? An equation may be represented using the matrix form. For example, if we have our equation 3x1 plus 5x2 minus 4x3, then this equation can be represented in terms of matrix by writing our matrix of coefficients 3, 5, minus 4, and the matrix of unknowns or the variables x1, x2, x3, which means that this matrix is our row matrix or row vector, and this is our column vector. Okay, and this is the matrix of coefficients, and this is our matrix of unknowns or matrix of variables. So given any equation, we can simply rewrite it in the form of matrices by splitting our matrix of coefficients as the row matrix and matrix of unknowns as the column matrix. For example, if we are given the same unknowns 3x1 plus 5x2 minus 4x3 is equals to 25, then this equation can be represented in terms of matrices. How? The left hand side will be separated in the matrix of coefficients and the matrix of unknowns, where the row matrix will be the matrix of coefficients, the column matrix will be the matrix of unknowns, and now the right hand side, on the right hand side there should be a matrix because we are writing our equation in the form of matrix equation. So there should be a matrix which is a square matrix of order 1 by 1. And we can verify that if we take the product of this row vector with our column vector, we obtain our left hand side of the equation. How? Our row vector has order 1 by 3, our column vector has order 3 by 1. So multiplication is possible, that is, the number of columns is same as number of rows, and the resultant matrix will be a matrix of order 1 by 1, that is, C will be equals to C11 only, which means that multiplying the first row with the first column, we obtain 3x1, 5x2 minus 4x3 and adding them, we obtain our left hand side of the equation. This shows that given any equation or any algebraic expression in some unknowns with coefficients, this can be represented in the form of matrix by separating the matrix of coefficients as the row vector and the matrix of unknowns as the column vector. Using this concept, we generalize that a linear equation of the form a1x1 plus a2x2 and so on up to an xn is equals to b. We have a linear equation in n unknowns, can be written in the matrix form or can be represented in the matrix form as the coefficients will be separated in a form of row matrix. That is, we will have a matrix of coefficients a1, a2 up to an. This is our row matrix. The matrix of unknowns will be a column matrix, that is x1, x2 up to xn, and on the right hand side we have a square matrix of order 1 by 1 which has the entry b only. So our linear equation can easily be represented in terms of matrices. How? By writing the matrix of coefficients as our row matrix and the matrix of variables or unknowns as our column matrix is equals to our matrix on the matrix of constants on the right hand side. Using this concept, we can generalize the representation of system of equations with the help of matrices. How? If we are given a system of equations of the form a11x1 plus a12x2 and so on plus a1n xn is equals to b1, a21x1 plus a22x2 and so on plus a2n xn is equals to b2, and continuing we obtained am1 x1 plus am2 x2 plus an1 x1 an2 x2 plus ann xn is equals to bn. We are given a system of equations in n unknowns x1 x2 up to xn and n equations. Then we can represent the system of equations in the form of matrix. How? This can be represented in the matrix form as, first we will have our matrix of coefficients. Matrix of coefficients will have the matrix of order n by n, will have the entries a11, a12 up to a1n, a21, a22 up to a2n, and continuing we obtained an1, an2 up to ann. Then we will have our matrix of unknowns. This will be our column matrix x1, x2 and so on up to xn. And on the right hand side we have our column matrix of constants b1, b2 up to bn. Now if we look carefully, that we want to ask that whether this matrix multiplication is allowed or not. Our matrix of coefficients has order n by n. This is our matrix of variables or matrix of unknowns. This is a column matrix of order n by 1, that is n rows and 1 column, and this is the matrix of constants. And this is again a column matrix of order n by 1. That is n rows and 1 column. Now, if we want to simplify our left hand side, that is we have two matrices in the form of product, then this product is allowed. Why? Because the number of columns of the matrix of coefficient is same as number of rows of the matrix of variables. Okay, and the resultant matrix will have the order of rows of coefficients and the columns of variables. That is our matrix of constants of order n by 1. So given any system of equations, we can simply easily write our system of equations in the matrix form. How? By separating our system of equations in the matrix of coefficients, a column matrix of unknowns or variables is equals to a column matrix which is a matrix of constants. Let us consider the system of equations. 5x1 plus 3x2 is equals to 15 and 4x1 minus 2x2 is equals to 12. We are given a system of equations, that is two equations and two unknowns x1 and x2, and we are asked to write this system of equation in the matrix equation form. How we will write it? We have to, from this system of equations, we have to make three matrices. A matrix A of coefficients, a matrix B of variables, a matrix X of variables is equals to a matrix B of constants. Now this matrix B will be a column matrix and this matrix X of unknowns will be a column matrix, and the matrix A will depend on the number of equations and the number of unknowns, that is number of equations and number of unknowns. So our matrix of coefficients will be a matrix of order 2 by 2 because we have two equations and two unknowns with the coefficients 5, 3, 4, minus 2. Our matrix of variables will be a column matrix with two rows x1 and x2 is equals to our matrix of constants, which is 15 and 12. We can verify this by taking the product of the left hand side. The left hand side is a matrix of order 2 by 2 and 2 by 1, that is 2 rows and 1 column. Since the number of columns of matrix of coefficient is same as number of rows of the matrix of unknowns, we can take the product and the resultant will be a column matrix of constants of number of rows 2 and number of columns 1, which is 2 by 1. And we can take the product. 2 by 1 matrix will be obtained. How? By, we have only two entries, B11 and B21. B11 will be obtained by the product of first row with first column, which is 5x1 plus 3x2, and B21 with the product of second row with first column, which is 4x1 minus 2x2. So given a system of equations, we can simply transform it into the matrix equation and solve for the unknowns x1 and x2. In this example, we have taken the system of linear equations, but any system of equations can be transformed into the matrix equation. For example, if we have our equation 10x square minus 4x plus 50 is equals to 0, then this is a quadratic equation, and this equation can be transformed into the matrix equation. How? First, by obtaining the matrix of coefficients, which will be a row matrix, that is 10 minus 4, 50, and this matrix will have order number of equations, which is 1, and the number of unknowns, which is 3, that is one row and 3 columns. Then we will obtain our matrix of unknowns, which is x square, x and 1, and our resultant matrix, which is the matrix of constants, which is nothing but a 0 matrix. Now our matrix of unknowns have order 3 by 1, that is 3 rows and 1 column. So the resultant matrix, these matrices can be multiplied because the number of columns is same as number of rows, and the resultant matrix will be a matrix of order 1 by 1, which is this matrix. Let us consider one more example of system of equations, and then we will write the system of equations in the matrix form. We are given the system of equations as x1 minus 2x2 plus 3x4 plus x5 is equals to 100, x1 minus 3x3 plus x4 is equals to 60, 4x2 minus x3 plus 2x4 plus x5 is equals to 125. Then we say that this system of equations can be represented in the matrix form. That is in the matrix form, that is the form Ax is equals to B, where A is the matrix of coefficients, X is the matrix of unknowns, and B is the matrix of constants. How? Our matrix A will have order number of equations, that is 3, and the number of unknowns, which are 5. So our matrix A will have order 3 by 5. So the coefficients will be the coefficient of x1 1, of x2 minus 2, of x3 is 0, x4 is 3, and x5 is 1. From the second equation, the coefficient of x1 is 1, of x2 is 0, of x3 is minus 3, x4 is 1, and x5 is 0. From the third equation, the coefficient of x1 is 0, of x2 is 4, of x3 is minus 1, and of x5 is 1. And now our matrix of variables x, that is the column matrix of order 5 by 1, that is 5 unknowns and 1 column. 5 unknowns are x1, x2, x3, x4 and x5 is equals to our matrix of constants, that is the B matrix of order, which order? Now here the number of columns of matrix A is same as number of rows of matrix X. So the matrix B will have order 3 rows and 1 column. So the matrix of constants will be a column matrix of 3 rows and 1 column, where the 3 constants are 100, 60 and 125. So given any system of equations in any unknowns, or the system can be a linear system of equations or the quadratic one, we can transform this system into our matrix form simply by splitting the matrix of coefficients with the product of matrix of unknowns is equals to the matrix of constants. With this we end our today's lecture. What we have studied today, we have studied the matrix multiplication, that when two matrices can be multiplied together and what are their properties. Can we interchange the order of multiplication or not? We have already seen it with the help of examples. What do we mean by the equality of matrices? And this equality of matrices we have used in our matrix equations. Then if we are given a system of equations, we can easily transform the system of equations in our matrix form. With this we have some practice questions from section 9.3 and we end our today's lecture. In our next lecture we will study about matrices, particularly the determinants of matrices. Allah Hafiz students.